Welcome. This video is brought to you by the Aviation Training Foundation. It's designed to help students master the procedures for troubleshooting DC electric circuits. Our first video in this series explained the various types of faults in circuits, including opens, shorts, and high resistance, as well as the relationship between positive and negative potentials in a circuit. Before watching this video, make sure you understand these basic principles and how to use a voltmeter. In this lesson, we'll teach aircraft mechanics how to troubleshoot aircraft circuits, though the methods can be applied to any electrical circuit. The entire program includes 22 modules on troubleshooting and wiring, tailored for aircraft maintenance technician schools based on FAA Part 147 requirements. To perform this project, the following equipment is needed: a DC power supply, a DC voltmeter or multimeter, a schematic for each circuit, and a wiring diagram for each circuit. The first step in troubleshooting any circuit is to understand its normal operation. It can be as simple as turning on a switch to light a bulb or as complex as operating multiple components. We'll start with a simple circuit and progress to more complex ones. Our first training board contains 5 separate circuits, each independent of the other. Every circuit includes the same components: a positive source or bus bar, a circuit breaker, a single-pole single-throw switch, and a light bulb. Each circuit breaker is labeled with the letters CB and numbered 1 to 5, switches are identified with the letter S and numbered 1 to 5, and the lamps are identified with the letter L and also numbered 1 to 5. The schematic diagram uses symbols to identify each component with corresponding letters and numbers, and shows the connections between them. It helps technicians understand the relationships between components but doesn't show the physical location of connections. For that, we need the wiring diagram. On complex wiring diagrams, it can be challenging to see which component connects to which wire. You might need to use a marker or pencil to trace the current path. In our first circuit, the operation is straightforward: turn on the switch, and the light illuminates; turn off the switch, and the light goes out. A proper test involves pulling the circuit breaker when the light is lit to ensure the breaker isn't shorted. In every circuit, there is always a positive and negative potential. The previous video explained that these meet at the switch when the circuit is off, and move to the light or load when the switch is on. If the breaker is pulled with the switch on, the potential moves to the breaker, creating an open in the circuit. If the breaker is in and an open occurs, the potential moves to the open point. When troubleshooting, your job is to find where the positive and negative potentials meet. This isn't always done by placing a meter across the open. Instead, you'll connect one side of the meter to a fixed location and troubleshoot using a single probe. All terminals and connections on one side of the open will be positive, and on the other side will be negative. To troubleshoot, locate a known negative or positive as a reference. On an automobile or aircraft, the frame is connected directly to the negative battery terminal, making the entire frame negative. By connecting your meter to the frame, you now have a negative reference. Your negative meter lead must be connected to bare metal. A painted surface won't work. Once connected, use the red meter lead to identify positive connections by touching the terminal. Usually, the actual voltage value isn't important. We're only identifying potential differences. Let's examine circuit 5. According to the wiring diagram, turning on switch 5 should light lamp 5, but it doesn't. We need to trace the wiring diagram to test it. Starting at the positive bus bar at terminal 89, follow the path through circuit breaker 5 to the bottom of terminal 69, then to terminal 73, terminal 75, terminal 77, and the switch labeled S5. If switch S5 is closed, the positive potential moves to terminal 59, then to terminal 76, terminal 56, and finally to lamp 5. Connect your black meter lead to the negative battery terminal and test each connection for a positive potential. First check 89, and then check 69, and then 73, 75, 77, 59, 76, and finally terminal 56. If terminal 56 doesn't show a positive reading, switch your reference terminal. Place the red lead on the positive battery terminal, and now any reading with the black lead indicates a negative potential. If terminal 56 is negative, the open is between terminals 56 and 76. Source voltage will be present at the open. If the circuit has high resistance, less than source voltage will show on the meter and the circuit may still operate. High resistance may cause the light to be dim or not lit, but some current will still flow. Follow the path on the other side of the open through the bulb and check terminal 36 and then 38 through 40, and then finally terminal 20. The last terminal is called ground, which means it has a physical connection to the frame. All of these should show a negative potential. In actual troubleshooting, you don't need to check every terminal. Start at the load, in this case light 5, and test both sides for potential. There are 3 possible results: both sides positive, both sides negative, or one side positive and the other negative. If the potential is across the light but it isn't lit, the bulb may be burned out or the socket or socket wires may have issues. This is common in external aircraft lights due to vibration and corrosion. If both sides of the bulb are positive, the fault is on the negative side of the circuit. If both sides are negative, the fault is on the positive side. Testing halfway through the circuit can narrow down your search and save time. In the next section, we'll troubleshoot a more complex circuit using the same procedures.